Hello everybody, my name's Josh, and this is Project Blue Smoke Monster. Thanks for tuning in this evening. We've got an interesting stream for you tonight, I think. For those of you who have been following along, you're familiar with the continual progress being made on my new microcontroller trainer project and how we've been spending a lot of time really trying to master the power supply side of things. And let me tell you, it's been a journey. It's been a journey. Trying to get my arms around every requirement and consideration that goes into the power supply of this has been something. Let me tell you, it's been something. Well, I don't have the problem solved yet. We're still working on it, but progress has been made. So let's talk for a minute about overall design goals and what we're trying to accomplish. The microcontroller trainer itself has, let's see here. I'm looking for a good, there's desktop, bench camera, video device. It doesn't have the screen. Hang on. Let me get this tweaked. Right screen. Okay, cool. The trainer, minimize that for this. Okay, cool. Here we go. Maybe a linear power supply with a big ass transformer. Well, there are some linear components to this design, that's for sure. So what we've got, if we open up KiCad and look at the schematic that is taking shape. This schematic is not yet functional. It's not right. There are some issues with it, and I'm hoping to learn a little bit about how to combat those, tonight and in future streams. So, the moral of the story is this. I want to take some sort of reasonable voltage for the input. 5 volts, 6 volts, 9 volts, something like that. Some reasonable voltage. And I want to do 3 things. Number 1, I need a 5-volt rail. A nice, steady 5-volt rail with about an amp of capacity. 2, I need a nice, steady 3.5-volt rail, 3.3-volt rail with about an amp of capacity. Number 3, I want to charge and power manage an 18650 battery. And I want to be able to have that 18650 battery when it's not charging also generate a 3.3 volt and 5 volt rail, good for about an amp. That's the laundry list. If I could just buy the chip I want to use, this would be easy. I can't get the chip I want to use. The parts supply chain issues are real. And it'll be a year before I can get the chip I want to use. Rather than holding this project up, we're compromising on features and capabilities a little bit and designing something that'll get us by. Now this overall design is probably the 4th or 5th iteration of a power supply. And let me walk you through the basics. In concept, now I realize the schematic is not correct and there are some things that aren't going to work the way I intended, but we'll get to that. First, I want to take a meaningful input. Maybe it's 9 volts. I like 9 volts as a number. It's really convenient. So let's say I'm taking 9 volts in. We run it through an L7805. We're good for about an amp and a half on that properly cooled. I might choose a different regulator. And that's okay, but for the sake of conceptualizing this, understanding that the current requirements might not be met, but let's just focus on the voltage requirements for now because there's ways to solve that. That gives me a nice stable 5-volt source. We've got a little input and output, filtering with capacitors here, just some smoothing, but nothing super fancy. Nice 5-volt rail, and we call that 5-volt rail PSVN. PSVN I want to cut straight to the output when we have DC input power on this barrel jack. I want it to cut straight through. Obviously, I want the IC that's charging the LiPo to continue charging the LiPo and managing that. But if I'm running plugged in, I want to just run off of it, having the LiPo charge. Now, when I'm not running plugged in, then we're going to be running off the LiPo. But let me get to that in a minute. So, for the sake of basics, we've got a 5-volt rail here, PSVN. Now, that 5-volt rail can feed... I'm looking to see where I can show it to you at. Can feed to a rail called 5-volt N. And I'll tell you what I drew here, and it doesn't look like this design's going to work. We're going to do some simulation and try to learn a little bit more about what could make something similar to this work tonight. But the thought was, if I put a P-channel MOSFET in, if the gate was at 0 volts, meaning this was off, then we would cut through PSVN through the MOSFET to 5VN. Now, in reality, if this is off, this isn't at 0 volts, this is floating. So some issues there I have to contend with and consider. And it doesn't solve every problem that I want to solve. More on that as we go. But the theory was we would route the power to 5VN. 5VN, whoops, is down here. It's this power rail right here. And what it does, oh, I wonder if it'll let me hit the U key there and select everything. Yeah, all right. Anyway, that's the rail right there. So that's my 5-volt rail. You know, we're going to light my LED indicating power on the 5-volt rail. We then have a 3.3 volt linear regulator with a little bit of filtering on either side and a 3.3 volt output. So that gives me the dual rail outputs that I'm looking for. When we are running off of only the 18650, the battery, then the TP5400 IC is going to take the output from that 18650 and boost it to 5 volts, recreating that 5-volt rail and supplying power to that 5-volt rail. And then our linear regulator is going to, again, take us to 3.3 volts. So, design considerations. I would love it if this could be as simple as possible. I want something that's not super hot. You know, I can, sync these regulators, these linear regulators pretty well. I have minimum parts count, minimum complexity. We don't have a whole lot of switching stuff going on. I think those are positives to this design. We do have an inductor on this charge IC, but it is what it is. Now, this design as drawn won't actually do the thing I want it to do. But we're getting there. What some people have done, if you want to pretend that all of this does not exist for a moment, what some people have done is they'll take this PSVN rail and they'll run it through a Schottky diode down to the 5-volt rail. So that would look, I need to get a keyboard tray out here. That would look something like this. And I'm just doing this for the sake of visualizing. That would look something like that. Now here's the problem. Number one, that doesn't prevent voltage from going backwards through and into the output of the charging IC. So I would also need to do something like this. Okay? Yeah, something kind of sort of like that. But I don't want, and down here it's not as big of a deal, but still a consideration. I don't want the output voltage of this charging IC, which is 5 volts, to drop 0.7 of a volt through this, leaving me with only 4.3 volts. And the same thing up here. I don't want this to drop 0.7 of a volt, leaving me with 4.3 coming into my 3v3 regulator. That's not a big enough rail. I want a 5 volt rail. I don't want a 4.3 volt rail. So those are the design challenges that I'm battling. To that end, let's illustrate perhaps some of what's going on and what we are trying to maybe have as options to deal with it. But let's start by showing you the power supply in its current state. What we have is that exact circuit that I just showed you here. We've got an 18650 battery. Things are a little warm here. I'm trying to see, is my preheat on? Nope. The board's just, yeah, the board's putting off some heat. Board's putting off a little heat down there. Ooh, on the shunt resistor. Okay. There's a little heat being made here. That's the thing. Anyway, what we've got is we've got our 18650. And that's something I need to look into because there shouldn't be a whole lot of load on this thing right now, like any. So why is it bloody hot? But we've got a couple of LEDs lit up here. We've got up at the top, this is our 5 volt rail. This is our 3.3 volt rail. And this is the LiPo indicating charging. Actually, I think it's indicating charged. I'll have to look into that. We also have, what was I going to show you? Oh, okay. We also have a LiPo inserted. If I pull the LiPo out, let me power cycle this thing and make sure that it comes back to the same state there. Yeah. I don't think it had detected it yet, but now it's in a standby state, so it's not actually charging the LiPo. But if I pop the LiPo back in, you'll see it detect that, and it should start charging the thing again. I don't know how quickly it detects it. Certainly doesn't seem to be at the moment detecting it. Okay, well there it did when I pulled power. So some kinks to work out. But, you know, you'll see we're getting a couple of rails there. And yeah, something's getting super hot here. So problem with this, the voltage outputs are not where we want them to be. Not at all. I'm going to fire up my meter so I can take a couple of measurements. And you guys won't be able to see this, but I'll tell you what we're seeing. So this is with the supply on. My 5 volt rail is at 5.79 volts. My 3v3 rail is at 3.29. So the 3v3 rail is fine. That 5 volt rail is too high. 5.79 is not where I want it to be. Now if I pull power, we're no longer charging the LiPo. We're just running on battery. Now my 5 volt rail is at 4.94. I'm happy with that. And my 3v3 rail is at 3.29. So those rails are perfectly acceptable in that configuration. But we're discharging the battery. Now, how does this work? Well, you remember I told you about cutting through another diode? Well, I've actually done that here. I've got where this purple wire goes. Let me see if I can move this just a tick. Where this purple wire goes, I've got another diode. So what's happening is the input voltage right here is going through this diode and bam, right onto the 5 volt rail. Now, like I said, there's no protection from this going back into the IC, which we don't want. So that's something that I would have to solve with that design ideally. But more importantly than that, the output voltage is ridiculous. That's not what I'm looking for. I can't do that. And the supply we're using is a 6 volt 1 amp supply. So 6 minus 7/10 of a volt is like 5.7 or something. And what did I say my output was? It was right about 5.7, wasn't it? Let's do that. Check again. Yeah, it's right about 5.7. So the math all works. I know why it's behaving the way it's behaving. I'm simply saying it's not acceptable. So what am I going to do about it? Well, I'm not sure yet. I'm going to think through some options. When we run on battery, we're happy with our levels. Could I drop the voltage more? Another 7/10 by going through a second diode? Yeah, I could. And that might be the simpler solution. The problem then is the output from the TP5400 is going to flow through that diode, and it's going to drop 7/10 of a volt. So I think that I'm shifting the symptom if I just add another diode. If I neglect to add another diode, then I'm not adequately protecting. Let me go back to this other picture. Then if I do that, then I'm not adequately protecting from backfeeding this V-out pin on the TP5400, and that could have some unintended consequences. So like I was showing you, if we go and were to do something like this, okay, Control Y. So if I added something like that, that gives me, it cuts the voltage through. And if I did this, it would basically give me 5 volts. But it doesn't protect me down here. And I would need something, somewhere like that to protect it from feeding backwards. And then that's going to then drop V out another 7/10 of a volt before it goes here. So yeah, that's not what I want. Now, if I had it doing it after, if I took it all the way to like here, it's tight. But let's say I put it somewhere like that, then I still have my 5 volt rail up to the point of the regulator. But that takes me basically to, actually I would have both. I would do this. I'd do that one more time. I would have this, and then that. Let me pretty this up. And then we'd be something like this. Now that would give me about 4.3 volts going into a 3.3 volt regulator. That might be enough. That might get the job done. But then again, it might not. Oh, and hang on. Wait a second. Take back what I just said. Hey there, Acid Deluxe. I could do something like this and actually bring that in here on this side. In fact, that's what we'd want to do. And even we do something else. And even move this over here. And then this back a little bit here. But you know what, actually, we're starting to get into other issues here, because I don't want that. I want this here, because it's for this, and then that comes over here. We'll see what this looks like. Let's see if it gets me close. This isn't the direction I think we're going to go, but I'm kind of curious to sketch it out to help me visualize it, because I'm a very visual person. I've got to see it in order to follow it. All right, so if I did something like that, that takes 6 down to approximately 5.3, and then down approximately, what, 4.2, 3, 4, 5, 6, 7, 8, 9. No, that's not right. Somebody that's good with counting with your fingers, let's see here, calc. 5.0 minus 0.7. So 4.3. Oh, I'm sorry. That'd be 5.3 because we're starting at 6 volts. Let's clear that out. So 6 minus 0.7 takes us to 5.3 minus 0.7 takes us to 4.6. So the question becomes in that model, is 4.6 enough to satisfactorily A, provide for my 5 volt rail? And actually this would need to move too. I didn't see it before. Is it enough to sufficiently provide that output? I don't think so. I don't like it. I think it's too far away. I think it's too far away from my goals. What did I say? It was 4.6? Is 4.6 close enough to 5? In my head, no. So all these things I just showed you, I don't really think they work. I think one problem introduces another. Solving one creates another. And it's just not the right way to go about solving this. So how do we do that? Well, that's what we're going to explore. So before I do that, let me shut this power supply off that you guys have been seeing. And I think we're going to do a combination of research and simulation and see exactly what options we have. Let me change operating positions, and we're going to go over to the desk. And boom, like that. And let's see what we can do to try to experiment, learn, figure this out. If you're just tuning in, thanks for jumping on it, guys. My name's Josh, and this is Project Blue Smoke Monster. We're doing some problem solving in the power supply design world for my microcontroller trainer. This is a dual output power supply that gives us a 5 volt rail and a 3.3 volt rail, and also has a battery charge controller, a TP5400, managing a LiPo, an 18650. So we're trying to get everything behaving with the voltage levels we want. We're going to need to do some circuit simulation. So I did a little Googling and came across something that I thought was really interesting. And let me find the link real quick. It is, let's see here. It's not the Arduino forum. Well, I'll just do this. Load sharing power supply design. And let me see if I can find the article that I read. Was it CUI's article? No. All right, hang on. I had a link to something. Do I have a second one to open? Yeah, here we go. Microtype.io. We'll see if it's this. I think this is the article. So this was put out by Kyle Hunter 6 months ago. And certainly Kyle, 6 months ago, was aware of the parts shortage that we're dealing with now. And he talks a lot about how to address this. So he starts off with, what honestly I've done a lot of, not with LiPos, but with traditional sealed lead acid batteries over the years. And you would simply have you'd have a charger, trickle charging your battery, and it would parallel your output. Now, that can work with, certain battery chemistries. I wouldn't advise that for a LiPo. As he'll talk about, you're blind to what's happening between the charging IC and the cell. It's just not a good scenario. So what he goes into talking about is how you have some options for dealing with this. One, disable the system load while charging. So this concept is what, in my mind, I thought I was trying to do here with this configuration, but it doesn't exactly do what I would want it to do. Because, where I thought to myself, well, this is at 0 volts, so since this PSVN line's at 0, we're going to, have this pulled low, and we're going to allow PSVN to pass through to 5 volt in. But the thing is, it's not at 0. It's not going to be at 0. That's floating. So that's a problem. I would need to pull it down. And if I did that, that would probably trigger the switching that I'm looking for. But I don't think it fully solves the problem. One, it doesn't protect from this issue with backfeeding into V out, so that's still a thing we have to think about. And so some things to consider there. So I kept on reading, and option number 2 really kind of struck me and said, I'd like to learn more about how this might work. And basically what he says is have the load take input power while charging. So basically we're passing the input supply to the load through a diode, this D up here. Well, that's what I was doing already. But you know what? I'm still up against that voltage drop. I'm still dealing with losing 0.7 of a volt there, and I'm not okay with losing 0.7 of a volt. At least not like that. Now, if I'm starting with like a 6 volt source and I'm dropping it to 5.3, okay, then we can talk. But 4.3, no way. Not what I'm looking for. So thinking about what this might behave like, and basically what's happening, and I want to mock it up so I see it, but you're having back-to-back MOSFETs here, and it looks like they're both P channels, and you're going to prevent the input supply from charging the battery through the diode. So basically this is going to block current going in that direction, but allow current flowing in this direction. So let's play with that and see what it does at different voltage levels. Now I'm trying to remember, do I have a circuit simulator on here? I don't know that I do. I have one on my Mac, but let's do this. Is it Circuit Simulator free online? Circuit Lab. Let's use Circuit Lab. Let's try to learn a thing. All right, and I don't know if I've used this one or not. I don't really have a favorite yet. So let's do a new simulation. Let's take a voltage source and bring it out here. And we're going to say that it's 6 volts. And let's see if this thing's got, there's BJTs, MOSFETs. Here's a P channel. Here's a P channel. Okay, good. And can I rotate this? Yeah, rotate clockwise. Rotate clockwise. And then flip horizontally. Okay. Let's see if we're close to mimicking that. So diode points to the right, tied together on the right, in the middle. Okay. So it'll be like this. So something like that. And let's put a wire from there to there. And then we're going to tie those together through a resistor. Cool. This kind of makes it nice to model. This is kind of pretty easy. And then close that one. He's pulling that up, and then there's a diode. Okay, so that's going to be this side of our voltage source. And then that's our charging IC, okay. And then our load's over there. And then there's ground. So what I think I'm going to do to simulate this is bring a wire from here. Never use this circuit or never use this simulator? Maybe both? Does it support an image? Oh, dude, that'd be cool. I have no idea what it supports. I'm game for using others. Here's something that says custom image. Let's do this. Copy. Save image as desktop. Let's call it C1. This feature is not available while you're trying the demo. Okay. That's all right. We can live without that for now. So then we're going to have measurement here. We're going to do a voltage measurement. Here we go. Voltmeter. Right here. And then this is where I have to try to not get confused. That's to load, that's ground. Those come together, okay. So that and that. Okay, so I think mostly that's there, and then this one, that goes to load. Oh, nope, not that one. Not like that. We'll go like this, and then we go like this. There we go. And then I'm going to put a voltmeter over here, because that's going to demonstrate what would feed back in. Let's see what happens here. So, how do we use this thing? I don't know what build means versus simulate. Simulate. DC. Click any wire to measure voltages and currents. I don't know that I see what it's doing here. Does it make me weird that I put a current limiting resistor on a fictitious LED that doesn't actually exist? Okay. Simulate. Does not have a ground. You sure you don't need one? I don't really need one. I mean, I just want it to run. I don't think it's turned on. PC simulation failed. This usually means your schematic is not a valid circuit. Look for unconnected, blah, blah, blah. All right, maybe it doesn't understand ground. So how's this deal with that? Well, let's... It's not exactly a node. Let's see what happens. Circuit does not have a ground, so it doesn't like that. Okay, back to build. Let's get rid of this. How do I add a ground? Battery. I don't understand. It's VM1. They are... One of them is going to measure the output. Oh, and I'm missing my diode. I got to add that too. One of them is going to measure this side of the MOSFETs. This one's going to measure that side. Because what I'm expecting to happen is have voltage come this way and down and light him. And this shows 0. Based on this going high or low, then I think that might alternate. But I'm not really sure. I'm curious to see the answer to that. But that did just identify that I forgot my diode. That would need to go here. Okay. Simulate. V, ground. Circuit does not have a ground. I mean, it does. Does it just not know it? Build. Edit parameters. No. I don't know how to add a ground. Ooh, there. Okay. Let's see what happens now. I think it's running. It's green at least. Let's try something simpler. Try something simpler. And I wonder if it'll deal with it in the same deal. So let's say that that's a battery. Register to continue? You mother. Alright, fine. Seriously? Alright, this sucks. Bald Engineer, what's a good online simulator that's easy to use that I won't spend all night learning? False Dad, thank you. Alright. I'm looking to see what we've got here. Yeah, I think that's going to do it. Okay, cool. New blank circuit. Let's add we're trying to learn how to build a little bit of intelligent switching into a power supply that I'm designing to allow me to switch, basically do load sharing between a LiPo and an input source while maintaining a solid 5-volt output and not either losing voltage when coming from the battery or losing voltage when coming from the wall wart. So what I'm trying to simulate is this circuit to understand a little bit about the functions of how those two MOSFETs are going to behave. 2 P channels back to back. Okay, add a voltage source, 2-terminal voltage source. Okay, click. How do I do that? Ooh, did that just work? Nice, edit. Is there like properties? Yeah. Dude, there is 6. This is easy to use. Nice. I like it. All right, so there's voltage source. Draw. I just want to play with this since I've never used it before. That's a circuit. Run, stop. Has no resistance. That's kind of cool. So it's smart enough to know that that's not a good idea. Well, let's do this. Add a resistor. All right, and it shows me 6 volts. Okay, cool. Cool. Yeah, that's useful. That's totally useful. All right. Well, now that we kind of know. Ah! Okay. Delete. Okay, so there's a 6-volt source. We're going to add a couple of P channels. Oh, dude, I can just hit P. P. Did that just work? That is not right. Oh, capital P. Okay, so there are 2 of those. How do I, like, rotate things? You grab the square and move it down. Oh, okay, well that's useful. That's close. Is there a way for me to mirror it? Because it's backwards of what I want to do. Oh my god, I keep drawing them. Or do I just have to deal with it with wires and labels? Labels. Okay. Let's play with it. Let's add a wire between there and there. And then let's tie... We're tying the sources together, basically. If I understand that. And then this will have a resistor. And then that'll go to here. We'll bring ground down here. And then We're going to add a diode. Like that. Whoops. I don't get the moving thing yet. I think I need to use keyboard stuff. All right, draw a wire. So that through here, basically to there, and then, nope, not that. That wouldn't be right. It would be that. And then that's ground. And then I want voltmeter scope probe between there and there, and then between there and there. I think that's it. Run. Okay. Well, I see my first problem. This ideal diode has no voltage drop. So, edit. I don't know that it's smart enough to let me do that. I want to tell it. Well, here we go. There's a shotkey. Two bad connections. What are you talking about? Run. Oh, is my battery backwards? My battery's backwards. Yeah, I think it is. Nope, not there. About that. There we go. Okay. I need to add a switch. Because right now that's hot, isn't it not? That's at 5 volts. That's at ground potential. Okay, we're getting there. Push switch. No, not a push switch. I just want to switch. That didn't work. Delete. There's the switch. And then wire here. Wire here. And then a resistor from here to ground. All right. Run. So we're showing in one state 5 volts there and 5 volts there. Well, that's not ideal. What happens if I toggle the switch? Okay, 4 bad connections. What's it mean, bad connections? I don't know what it means about bad connections. Is that maybe what that little red means? Whoops, delete that. The world's tiniest little resistor. Let's see if deleting a few things clears those. Yeah, it's clearing those bad connections. Oh, okay. Do you know any physics? No. Definitely not. Okay. Now we're getting some connections here. I am seeing a little bit more about what it doesn't like. So it literally doesn't like to snap things. Okay, well, we can work with that. Go here. Will it deal with it if I do that? No. Wow. It literally wants me to draw it a segment at a time. Okay. Well, at least that's working now. All right, run. Oh, still need another resistor. Yeah, it is kind of a neat little app. I've never, well, I don't know when I say never used it before. I certainly haven't used it any time recently, but we're just trying to do some basic circuit simulations. There we go. And then draw a resistor here to there as a pull down, and then draw a wire here to here. All right, so that appears to be our circuit. Run. Doesn't look like it does what I would think it does. Let's look back at their original schematic. So those are pointing at each other. There to there. Howdy, RJ. How much does it cost to print a circuit board? Simple PCBs can be just a couple of dollars for a couple of inches. You know, 100 millimeter by 100 millimeter is kind of a popular size that a lot of the board houses will sell for just a few bucks. So RJ, we're trying to do a little power supply experimentation. I'm trying to figure out how to bring some smarts into the routing of power in my power supply for the trainer board. And I found this little article talking about putting a couple of P-channel MOSFETs back to back. So I'm trying to learn a little bit about how this is working. Oh, and that's a pull down. That's a pull down to ground. Okay. So that's what I have. So we're trying to simulate it and learn a little bit about how this is working. So that's a voltmeter. What do you mean one bad connection? This thing's a bad connection, it says. You're a bad connection. Add a wire. There to there. And then there to there. Okay. How about now? All right. Now we got something. Okay. Well, that doesn't exactly look like what I'm looking for. So where did I go wrong on the circuit is the question. That's V-bus. Measure to ground. And that measured to ground. So what I'm expecting to see that's not happening is I'm expecting when this is on for one of these to be 5 volts and one to be 0. And then when it's off, maybe they switch? But that's not happening. So where am I going wrong? Pulling that down to ground. Oh, hang on. I think I might see it. That's ground. That's where they're tied together. Okay. And then one. No, that's right. That is the intended circuit, as far as I can tell. Those are meters. Those are just test and measurement points. A voltmeter, basically. I don't think those work how you think they should. I don't think they work how I think they should either. So this is showing power always coming out here. Oh, well, hang on. Maybe I'm thinking of it wrong. Let's leave power on. Do I have an open, or you're just talking about when I disconnect the switch? Isn't one of your MOSFETs supposed to be connected to your battery? In this example, the battery is just a DC source. It's not actually the battery that I'm talking about. I'm just trying to understand how these things are doing what they're doing. How is the drain on the left one open? Did I connect to the wrong place? Isn't that drain the meter? Oh, the meters are opens. Oh. Okay. I see what you're saying. I was not realizing that. So then I should do that here and here. And then let's edit those. Don't use them? Okay. Turn on the voltage for the wire. Let's do it. Whoops, not that. Who likes my crooked little resistors? There we go. That's not what I wanted to do. I can't see it. Oh, view in new scope. Oh, sweet. Yeah, that's kind of what I was looking for. That's super cool. Super cool. Okay, so click on the wire. You can go to, say, show voltage and show current. I'm not sure. The buttons you say are supposed to be there are not there for me. I can just hover it and it shows me 4.5, 0. Right click on a wire. Yeah, I don't have a show voltage. Select edit. Oh, thank you, sir. That, oh, cool. That's super awesome. Thank you, sir. Appreciate that. Edit, show voltage, which should always be 0. And then thinking here. I really want it to be there, but I can't do that. Let's edit that as well. No. Probably wants that, doesn't it? Yeah. Okay. But I don't actually have a wire there. So I'm going to do this. Well, that does show what I'm looking for. That shows me that I do not have voltage here. Okay. Oh, well then you know what I can do? Ooh, there's a better way to do this. I see a better way to do this. Okay, let me try this. Please tell me it has. Aha. That's ground, that's hot. Awesome. Okay. Yeah. Let's see if I can draw it correctly. There. And then there. That's ugly. And then there. Shows 5 volts at the output. That's roughly what we're talking about have happen. We're going to have an output, but we need it to block. I mean, I think it's showing me that it is blocking it. Before I added the switch, we didn't have any voltage there. But if I put voltage there, we're getting 5 volts on the output. That might just do it. That might just be a meaningful way to do this. Okay, well, I think we see how it's behaving here. Let's take the next step and try to put that logic into our schematic here. So let's get my brain turned on correctly here. And let's move a few things around. Let's move this out of here. All right. So we're going to do something like this. We'll just move these out of the way for now. And then we're going to go like this, and like this. And then we're going to take this to here. And let's think about where this connects in the circuit. I'm looking at it and I'm having a problem in my head with this. But we can talk about it once it's drawn and see if we think this is at all close. And then this, and then this. And then that. So that is V out. So I think what has to happen is let's see if I can get this stuff all fit. So I'm coming out of here, and then there, and then here, and then there. No, I don't think that's right. Back to my other drawing. That's the V out, and that's the load, and that's the ground. So their configuration's a little different here in their charging IC design, but I'm still thinking I can maybe adapt that. Because really, I'm just using the switching properties here. R1's pull to high. If we're pull to high, then neither one of those MOSFETs, those P channels, pass voltage. When we pull low, then they do. Okay. How are they dealing with that here? They're pulling that to ground unless it, okay. So they're doing this. Actually, I can do it here. So they're doing that. They're saying, pull it to ground. Pull it to ground when there's not power coming in. That prevents this from floating. Okay, that needs to be on the other side. Then this goes over here. And does that not come back down? I think it does. I think that comes back down. So from here to here, all right, I think that is what it was trying to show me. So let's think through the logic here. Power comes in the barrel jack at, 9 volts. We drop it down to 5 volts. We've got a nice clean 5 volt source here. That's another drop still. All right, well let's talk through it anyway. That's gonna drop 0.7, so we're at 4.3 here. No, it's not. Yes, it is. Yes, it is. Because of the 7805. Okay, well let's assume that's not there. What if it's a 7806? Okay, a 6-volt supply coming in. That drops at 0.7, so that takes us to 5.3, which I can live with. I can live with 5.3. And this can tolerate 6 in, I believe. The TP5400. Let's see what she's rated at. I think it'll do 6 volts. VN5 there. Input voltage. That's good to 10 volts. Okay. So 6 is not hurting him anything. So 6 volts coming in. And yeah, I know a 7806 is a weird part, but we can address that in a different way. But let's just show it's 6 volts for now. So that gives me 5.3. So let's make a little note here. So basically we're 5V3 there. That is plenty of voltage for the 3-volt linear regulator. We've got a blocking diode keeping it from going back into here. When this is powered and we're discharging from battery, then we're at 5V here. On that rail, which this is low because of this pull down. So this will go pew through both of those, hit here, and it's 5 volts out. I feel like that does what we're after. Does anybody agree, disagree, think I'm an idiot? I feel like that has potential. And I can live with 5V3. And we could even tune that. Put a test point on every node. You're not kidding. Yes, there will be. And we'll have to build this to see if it works, but I think that certainly has potential. You know, I need to buy some of those. I haven't got any of those yet. But you're not wrong, because we want to be able to inject power too in stages, not just read it. Okay. You're going to make me buy some of these bloody things. Actually, you know what I need to know? The board house is going to build this board for me. Oh, you're saying just pads? Okay. I was going to say I need to go see what my board house has for test points in their inventory. Because I'm sure they have a few things. Show me basic parts only. I'm sure they don't have any basic parts. Yeah, I didn't think they would. All right, those in stock. Can I sort by stock? Oh, yeah. Yeah, something like that. Yeah, something like that. 50 cents a piece. It's not horrible. Test SMD is what they call it. Okay. Manufacturer Keystone. I wonder if KiCad's got anything for that in there. Let's look. Is the design at least plausible? I think we're seeing that it may be. It's going to cost me $50 to spin these boards, so I want to get it right. I think it feels plausible. All right, let's put some test points. Bah. All right. You're not convinced the source pins of the FETs are doing anything. Okay. I think all that it's doing is creating a circuit, is it not? Does it look better at that? Or I think what I'm interpreting is that it's just closing them both when this is pulled low. And that keeps it from going this way, and that keeps it from coming this way. I mean, it begs the question, why wouldn't just one P channel do it? Because that means they're floating together? Okay. Well, you know, the good thing about this is, if we needed to, we might build some ability. I mean, we pull this resistor, and we jump these together, and we can disconnect. You know, we can put some pads in and allow ourselves to kind of bypass things if we need to. Okay. Well, this will be fun to experiment with. Yeah, he says the second change, so replace the diode with a MOSFET ideal diode. A MOSFET ideal diode. I mean, what is the difference between a MOSFET and a MOSFET ideal diode? Oh, you can replace the diode with a MOSFET ideal diode to reduce the voltage drop. Well, you know what? That was another problem I had. What in the hell is a MOSFET ideal diode? I mean, I thought an ideal diode didn't exist. If that's a thing, then maybe some of the diode solutions can work. Let's Google. Basics of ideal diodes. Are we simply using a MOSFET as a diode? Is that what we're getting at? Basics of ideal diodes. Yeah, this looks like something I should read. Power shotkeys are used everywhere. Yes. Yeah, circuit that overcomes the voltage drop. Yeah, exactly. Because that's the problem. I don't want to read the whole thing. An ideal diode controller drives an external N-channel MOSFET to emulate an ideal diode with very low forward drop and negligible reverse current. Yeah, so that's what they're saying. Ideal diode control. See, we're getting into way more than I want to get into with that. This is a TP5400 is the charging IC. Yeah, see, I don't want to get into all these parts to make a, quote, ideal diode. I think we live with the voltage drop, and we feed it 6 volts. Okay, so back to this. That's their little test point, test ring, blah-de-da-de-da-de-da. Let's look at his data sheet and see what his footprint looks like. Yep. That's it? Okay. I thought maybe it would specify its pad, but it doesn't. Oh, yeah, it does. Up here in the left hand. I didn't see that. Okay. 0.135 by 0.70. Okay. Well, we'll see if we can make one of those. KiCad. In here. Test point. Good enough for me, man. There's one. We're going to put one here. We're going to put one here. We're going to put one here. We're going to give ourselves one at ground. We're going to put one here. We're going to put one here. We're going to put one here and here. Even if we don't need them, we'll put $50 for the test points on this thing. Okay. And what the hell, we'll put one here. Okay, for the purposes of this, we could eliminate that regulator because I don't think my board house is going to have a 7806 in their basic parts. We'll come back to that in a second. Actually, the 5017, it's in there, so we know the part number. Okay. L7806. Extended part. I mean, they do have it. They have it as an LDO, a TO220-3. I mean, we're not going to get into through-hole stuff, though. I can just do that here. I'd want something, you know, something like that if I were having them assemble it. There's no stock, though, so we need to look for in stock. Yeah, okay. We've got some options there. It just scares the shit out of me designing against something that only has 950 components available in the universe. Okay, but it's just 6-volt regulator. So the other thing we can do, if we didn't already, is do one here and do one here. We can always bypass this stuff. Okay, I like it. I like it, I like it, I like it. God, that's a bunch of test points. Alright, let's hit save. So anyway, that's kind of what we're looking at. It's coming along. Singing a song. Yeah, cool. Thanks for everybody just tuning in. My name's Josh and this is Project Blue Smoke Monster. We're working on designing a power supply for a microcontroller trainer project of mine. And we can kind of show you a little bit about what it's looking like so far. We've just added a few components to it that we've yet to put on here, but we've got an 18650 LiPo cell. And the goal is to use a charging controller to produce, to power the charge of the LiPo and discharge and manage all that. And also to boost the output to 5 volts that we then step down into a 3v3 rail. So we'll have the 5 volt rail, we'll have a 3.3 volt rail. We've got some current shunt resistors that are going to be measuring current consumption with an INA 4221, talking I2C, to a TTGO T-Display microcontroller, which is an ESP32, with a really nice IPS screen on it. This is ultimately going to go onto a bigger project, but we're trying to get the bugs worked out of the power supply first. We did one spin of it, learned a few things, found some successes, had some not great successes, and we're going through making some revisions. So, back to schematic world, we need to create a footprint for that doohickey. Footprint editor. Ooh, wait a minute. Keystone. Test point? What was theirs? A 5017? We might actually have something real close. Yeah, 5017. Okay, well, let's see what this thing gives us. 5015, 5019. Because there's a 5019. And let's see how big that is. 3.8 millimeter by 2 millimeter. 3.43 by 1.78. Well, it would fit on that, but let's go ahead and edit it. 3.43. I'm going to do this. Save a copy as. Go up into mine. .501.7, and then we're going to go here and edit it. 3.43 by 1.78. Okay, just a little smaller. Save. There we go. So now, if we want to go into KiCad, back to here, we need to do a little footprint assignment work. Let's annotate the board. And get into our test points. And this is going to be in my library. And that one. Fill those in. That's an L7806. Thinking, do I want to put that in the circuit right now, or do I just want to leave that off? If I leave it off, I can just put a regular 6-volt regulator into it. Nah, we'll put it in there. I can always bypass it if we don't want to use it. All right. So which one does the board house have? Their L7806 is a TO263-2. Did I say a 263-2? Sounds about right. 263-2. Okay, and then we'll need to look at the data sheet for pins. We're in the D squared pack. Pretty sure. I think that's what they call the D squared pack. Let's see what we've got.
Sorry.
Let's see here. Pretty sure it's the D squared pack. Yeah, because that D pack's even smaller. We're a D squared pack for sure. Yeah. All right. So input, ground, output. So then here, tab pin 2. I think it's that one. And we'll look at it and make sure it looks like it's right. here to there. Okay, so that should do our footprint assignments. Now if we bump over here and we go redraw, update. Pretty close. Pretty close. All right. We got a little work to do there, but pretty close. Let's move some things. There's a couple of MOSFETs. We'll figure out what packages we're going to use there. We said we were going to look at this. Let's look at that now. So 1, 2, 3. Pin 1 is going to be our input, and it goes, yeah, that's our input. So 1, tab 2. Does that match the data sheet? I think we're right. Ground, tab 2, input. Yeah, that works. Okay, cool. So get into a little bit of layout here. So this is what she looks like right now. Let's turn that pour off so you don't have to see that. Pretty straightforward, not a whole lot going on. We've got our input starting right here at the DC jack. We run through this little doohickey. We'll make some changes there. I'm going to drop a fuse in there. It is a resistor, a really low ohm resistor, just to give us some short circuit protection. But I'm going to go ahead and drop a little fuse in there. And then that comes over this way and, you know, starts feeding into our LiPo charge controller. So if I'm going to have an upfront regulator, we can put him right over here and be just fine with that. That stuff's a little tight. Let's see what it looks like on the render. Okay, we're going to have to get a... No, we're not. It's already there. So that kind of shows placement. We need to create some heat sinking for this. But yeah, I think that's plausible to start with. A little tight, but we can probably make that work. So then we're going to go up to a really chunky track size here. And actually, this is going to be super easy. Go from here to that. Okay, so we need to do this. We're going to connect it actually on the opposite side of that resistor. So on R2. We need to replace R2 and get that handled. It's going to be a little fuse. So let's see what we've got in here. In fact, I've got some of those here in a bag. I probably won't have them provide it, but let me see what it is, and then I'll decide. Regulators, shunts. There's a little varistor. Those are bigger ones, or those are the tiny ones. So I want the bigger one. Here we go. Little fuse. Oh, those are monsters. Let's look it up. In fact, they have it. I'm sure they have it. Little fuse. 2920L 250DR. Not little fuser. Nothing. All right, well, let's do this. I may have to assemble the fuse. Let's see if I can find it. There it is. What's that thing rated at? 15 volts, 2.5 amps. That's great. That's actually really good. It's a 2920 mount. Let's see if we can do that in KiCad. I'm also not opposed to just leaving it out for now. What else is open? There we go. Little fuse. Seriously? You give me nothing? There's a polyfuse. Let's just do that for now. Because we might even just jumper it to start. But that'll at least get things connected. Edit. $25.20. That's probably good enough for now. Good enough for now. We'll confirm that before we build it. Save that. Pop back to here. Update. Good. There's our little fuse. Kind of a cool thing to call it, isn't it? All right. We'll drop it right there. To there, and then where's it want to go? It wants to go all the way over to that. Okay, getting there. So that's down to VCC. And then, oh, you know what? I'm going to move that. Actually, I'm going to put that in a different place. This is going to work well. Not a major move, just a little move. You're getting an ad to download the Unreal Engine. Are you going to become a game maker? I am the game master. Okay. Okay, there we go. That's pretty awesomer. Okay. And try to route that. Blink. No, doesn't want to do it. What, now it wants to flip? Rotate. There we go. Blink to blink. Okay, those are connected. And much better. Okay, so there's our polyfuse. Let's render that. Yeah, we'll have to screw with footprint because it's a little wider than that, but that's okay for a start. All right. That flows to our regulators. And why is that showing it as pad 3? Pad 3. Input. Okay, back to the schematic. The output goes to the polyfuse. Oh, okay. The barrel jack to the regulator. Oh, well, that polyfuse is still in the wrong place. Okay. Brain fart. We want that to be over here. That's where we want it. Okay. Now I see it. Sometimes KiCad will even tell you what you're doing wrong. You just gotta listen. Bald Game Master. Okay. Now, will it let us route now? Of course, I've jacked it up again over here. Okay, rotate it again. Undo that, grab here. There to the polyfuse. Much better, young Skywalker. Okay, there we go. That's PSVN. That'll travel its way down. Okay, cool. Now the teeny little trace there. Yeah, we don't like that little trace. Gink. Okay. Okay, I'm happy with that. Our ground, we're going to pop a yeah, I like that. Okay, hang on. Let's go up to a 1 millimeter grid. Bang, 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 bang. This is good for thermal too. Get some nice heat transfer down into that layer. All right. Huh. I wonder how that got disconnected. Not sure what that's doing there. That looks a little weird. What is that? There we go. It's like it was confused at where it was supposed to go. All right, much better. Much better. Okay, what else we got? We got some test points. We got some MOSFETs. All right, well, let's get those MOSFETs down where they're gonna go. Well, they're not in the right packages yet. Okay, so we need some P channels. Let's see what the board house has and something that's suitable. Pride transistors, MOSFETs. Show me basic parts that are in the stock. $60. Let's look at this part. No, let's look at N channel. Not that. Let's look at this part. $10 volt, 4.3 amp. That teeny little thing. X1 PV. Let's look at the data sheet. $30 volts, 4 amps. Psh, okay. Now this is where I go back and I think about the things that I've learned watching content from the Bald Engineer. VGS threshold, gate threshold voltage. .5, .9, 1.3. So that's going to tell me that at 1.3 volts this thing's going to trigger. So that's pretty good. Pretty low. Means we should have no trouble. So the A, I'll write that down in KiCad so we know what the heck these things are. Edit. And we'll look at packages. What package do these come in? The SOT23 3-leg. Basically that. There's the part number. We're going to have to go back there. Seems plausible anyway. Okay. Here, update. Boom, that'll change those two footprints. We can pick those bad boys up and move them right where they needs to go. I don't know why I'm talking like that. Okay, a couple of MOSFETs. Boom and boom. We're going to be tying those together. Rotate. Rotate. Bonk, chunky. Okay, yeah, to a test point. Those are too big. Okay, that's more appropriate. Okay, I like that. Q1 and Q2. Peek at the schematic. Pin 3s are getting tied together. Which happened. Pin 1s are getting tied together. Cool. And we might even relocate this somewhere else, but that's where it's going to be for now. Okay, let's start moving these test points around. Ooh, and let's not forget that diode. Get that diode out of here. We know it's going to be over here near that guy. And then TP for my bunghole. Okay. Let's start getting some test points near things. PSVN. That's up here. Let's see what that looks like. I've never used one of these, so let's see what it renders like. Okay. So we don't actually have the unit, but I think we can make that work. Something like that. Yeah. Yeah. That's fine and dandy. So there's a test point. Let's start moving some other test points around. We'll just bring them near what they're doing. These things take some space. Put it here, and let's move this down there. And then this one. What's What's it near? It's near this thing here. That looks like a good place for it. 5VN. I'm digging that. PSVN. Wait a minute, I already have a test point on PSVN. I don't need that twice. TP2 and TP3? Yep, don't need that. Let's get rid of TP2. Okay, gone. What else we got here? TP11. More test points. You like test points, boy. Bald Engineer, you are challenging my layout skills. Getting this stuff tight. But hey, all right. That's on the polyfuse, or near the polyfuse. We'll put him right there. How's that look? Man, that one's just awfully tight. That TP3 has me a little nervous, but it'll be okay. Okay, what do we got here? That's easy. That's easy. That TP5 and 6 appear to be in the same place. TP6, TP5, oh they are. Don't need both of those. Okay. TP5, TP for my bunghole. Got it. Yeah, you're right. They can be almost nothing. You are absolutely right with that. Because they carry no current. That. And a nice ground one. You know what's cool about ground? We can put him anywhere. Like up here. Yeah, nice and convenient. We have a few other parts. We're not going to worry about them yet. Let's kind of see what she's looking like. Wow. That's a lot of test points, boys and girls. Cats and kittens. I'm not unhappy with that at all, actually. Yeah, I'm not unhappy with that at all. Let's look around and see what these other parts are. A 1.1K, R12. So there was at one point a 1.1K. We've done some refining of the design, and we'll have some more to do, but I've been finding the correct parts. I ordered the design with some weird parts because I was having issues navigating the board house's part library. On the ones you have room, yeah, describe them, yeah, for sure. I think we'll do that. Let's see what some of these parts are. R12. What is R12? That is just a ground. That's just a pull down. So that's new. Okay, edit. That's going to be a 1K. And it can go anywhere we want it to. Okay, this thing, what's it do? It wants to be down here. Oh yeah, okay, well that's not horrible. Yeah, right there, baby. And then that's just a nice power supply cap. Yeah. All right, where are we at? We have Yeah, probably quite a few unrouted nets. 27, that's not bad. Add a couple for ground. Yeah, I added one. I'm going to probably put a couple more on there. You're right. Because that's just so damn helpful. There, that gives me 3. Cool. Cool. What's up, Bellum? Yeah, we're iterating on the power supply design. It was small again, and now it's huge again. Oh, so we continue to defy logic with this power supply design. We've added some smarts to it tonight. Primarily, I've added an input regulator to drop me down to 6 volts. We've added a couple of MOSFETs and supporting components to effectively give us a bypass of the LiPo charge module. We're not totally bypassing it. It can still charge. We're basically doing load sharing. We're saying let the LiPo charge and let's power our circuit, and let's not let voltage feed back into the LiPo charger when we're bypassing it, powering our circuit. Yeah, cool. Cool. I think we're about there, guys. About there. We got traces to route, so let's do some trace routing. And like Bald Engineer was saying, these traces can be pretty small. They're not carrying anything all that heavy, so we'll just start making ties to them. I mean, I'll make them a little larger when I can, but there's no need to go overboard with it. Oh, oops. There. Whoops. There to there. That's a diode. We'll put some real wires on that. Because that's going to carry some current. Yeah, I'm good with that. And then, okay. Oh, and I don't have a ground pour on top. We might look at that in a minute. Yeah, that's not much to that. We can do that. A little more current on those. Nice. Oh, wait a minute. Wait a minute. Okay, better. 17 unrounded. Cool, cool. $15 unrounded. Let's bring the grounds in. Thinking here. That's better. Because it was angry there for a second. Okay. That's better. That was an error. That's a ground. Just link that over to there. That's just a test point. Let's do this. And then I can just go boom up to there. Those are some grounds. All right, I don't have a top pour, so we'll just let that happen for now. And then we'll bring this out to via. That's not what I wanted to do. Do that, and then we do this. Drop it, drop it. Drop it like it's hot, and drop it like it's hot. All right, boom. Draw it. 8 unrouted. Got a little doo-wopper down here. Bring that around. Those are just LEDs. They don't need to be big. Almost there, guys. Almost there. Was I Snoop Dogging? Sometimes I do that. Something there looks goofy. SCL, SDA. Something looks goofy there. I'll go back to it. I want to get the rest of these in there. Boom. 5VN. Can just go to there. Oh yeah, that's not right. We might have a naming issue there. We'll need to look at the circuit on that one. Unrouted 6, we're down to not much. Okay, 3v3N, that's just a test point. That's a ground thing. I don't think it's gonna let me do that, is it? No. Quit that. Cancel. Get out of there. Delete you. Oh, you piece of turd. Okay. Get out of there. Unrouted 4. Okay. So we're going to have to figure out what's going on there. So pin 1 of the TP5400, where does it go? There's a test point, and it goes over there. Okay. So yeah. So this is old. Nuke those. Let's bring it together. Here. 5EN, yeah, that should be fine. Okay. Okay, I'm liking that. Now that's still going to carry some current. That's all right. Again, we're not going to probably pull full current through this board yet. There's probably plenty of room for optimizations. All right, now what do we got over here on the 3221? Pins 6 and 7. That's got to be SDA and SCL. Yeah, so we're pulling them up through a couple of resistors to the 5VN line. Which is what those are doing. Or the resistors reversed. Pin 7 goes to R3. Yeah, those resistors are reversed. I probably swapped that at some point. But they're electrically the same, what they're doing. I'm just going to reverse them here so I don't have to screw with the board layout. That'll probably fix that. Total warning 0. Total error 0. J1 pin 3, we'll worry about that in a bit. But yeah, that fixed those. There's a test point that needs a connection. For the G round, right there, boom, via done. Unrouted 0, and draw it. I wonder if I can find a 3D image for that test point. Let's see. See if we can find a step file for it. So it's the 5017. Keystone 5017 step file. Yeah. Download step. Okay. And subscribe to our mail spam list. Are you serious? What if I just want to download it? Hang on. They're being annoying. Yeah, they want to be annoying. All right, I'm going to switch over, fill that out real quick. Not that any of this is super secret, but we'll fill it out. Plus, I don't mind getting their newsletter for this. Check your email for the code to enter to download the file. Oh, nice. Oh, yeah, no, I like Snap EDA for sure. Wow, that legitimately made what's probably an actual random code. Hey, we got a step file, though. All right, let me switch back. Blink. Here we go. There's the file. Show in folder. Copy. And And go back to the B drive. KiCad libraries, 3D models. New folder. Keystone test point 5017. Then over to KiCad. And here and edit. Add one. Browse it out here. Nuke this one. Boom. Now let's get our rotations in place. Ooh, dude, really? That's the first time I've only had to do that. That was way too easy. All right, and then edit. I don't know if it'll do that to all of them. Competitors, customers, employees. So would fill it out. Okay, let's do this. That probably was just the one. Yeah, it's just the one. All right. Blah. I wonder, is there a way for me to update that 3D model for every part? Because the 3D model is, I mean, yes, I can. I can do it like this. Let's go edit. No, not that. Edit. Copy. Edit the library foot. Oh, wait, you can do the 3D prop. Oh, okay, that's faster than the way I was going to do it. I didn't realize that a footprint stored the association to the 3D model, but that makes sense now that you say that. So there's that. But where do I go to tell it what the model is? I don't know how to edit the 3D properties. '3D viewer. Okay. So it's definitely a thing. Properties? No, not that. I go to part level. Edit. It's one of the buttons. Okay. Let's look. Over here, maybe? Appearance manager. That's that thing. What about up here? Footprint properties. Okay, cool. There it is. Hells to the yeah. Not that way. Actually, yes, that way. Save. Boom. And then go here. And then footprint. Update footprint. Update footprints with the value. Save it and render it. Yeah. No. Close. Very close. I think that's an issue with what I did in the other thing. Very, very close. I think I might have left the old dead one out there. Like when I added the new one, there were, I think, multiple selected. I jumped too fast. And if not, then I'll go do that other. But I want to make sure this is correct. Oh, what the hell? Well, that just crashed, KiCad. Sure did. All right. Open recent. This? Nope, not that one. Open recent. None of those. I crashed KiCad. Okay, footprint editor. That's fine. This. So you're like gear. What? Gear. Footprint properties. That one? Chip with gear? Yeah, so that was my fault. Although that looked right. Oh, I rotated it the wrong way. That's going to work though. So we'll edit it. 3D model. Not edit. Actually, I think I can just update. Update footprint. Because I'm doing it with a matching value, they all had the same value. So it should work either way. Let's find out if it did. Yeah, we're good. All right, cool beans. Look at that. Test points everywhere. And they look reasonably accessible. Nice. All right, cool. Well, I think that is, here in just a minute, we'll wrap things up, but I think that is tremendous progress. We're going to, you know, I'll go through offline some parts validation and make sure footprints are all good. Get this thing ready to spin back to the board house. I'll tell you the biggest mistake I made and why you haven't seen this thing on the board yet. I completely hosed the IC footprint for the microcontroller, but it's been corrected, and I'll triple check it before it goes out again. It was nowhere near pinned out correctly. I was off by the pin counts and everything else. So, but yeah, this is coming along. I think it'll give us, you know, the ability to do more testing, do a lot more measurements. I'm learning to finally use some test points. I like to go just DuPont, single DuPonts that I can solder in, but they kind of suck to solder. Plus, if I'm having the board house do it, these will just show up. So, Keystone 5017s. Apparently, that's what I'm going to standardize on, and apparently I need to go order like 100,000 of them. All right, cool. Well, I appreciate everybody for tuning in. I do want to show you real quick, if anybody wants to support the channel, patreon.com/BlueSmokeMonster. We've got a couple of tiers. In fact, let's go to the public page so you can see what we've got going on. You can support the channel. There's a PCB membership and a gold membership. Pretty cool things. If you're interested, you can get cool channel merchandise. You can get projects that I'm designing. You can get circuit boards. You can get full kits. Check it out. I would appreciate it. Even if you can't, I would encourage you to subscribe so that you're notified when we're streaming. I do expect to begin creating some more content for the Patreon people, some private, special, exclusive stuff down the road. But you know, the best thing you can do is show up. So if you can't support us through other means, support us by being here. You know, jump into chat. Tell me what we're doing stupid. Tell me what's interesting to you. Tell me, hey, doofus, you know, lay the board out differently. I like your feedback. It really helps evolve the product and the direction we're going. And I look forward to continuing it. If this is your first time watching Project Blue Smoke Monster, or if you are a veteran, we'll go ahead and show you a little bit about what you can expect to see here. Again, my name's Josh. Thanks for watching. We'll see you in the next stream. Holy crap. Did it just desolder itself? I think it's desoldering itself. One end of the coil goes to the antenna connector, jumps to the diode. The diode is our audio path, and this comes out to the headphone. One of these days I'm going to fix the squeaky chair on the screen. So if you want one of this rev, it's available to ship now. Oh yeah, can't do that here. Can't do that here. Gotta do that in the other part. Boy, I've got that heatsink hot. Like hot. Like feeling hot. I mean, this is not going to be a showstopper that stops me from developing this. If I got to deal with like garbage for this badass capability, I'll deal with like garbage. And the microcontroller trainer is a learning environment, experimentation environment, development environment. You come up with what you want to call it.